about a little bit yesterday. Velocity is one of the more important metrics to characterize in combustion systems. We want to characterize the flow field. And what lecture 4 is going to do, what we're going to do is give you kind of maybe not a background, but hopefully kind of a backdrop for why we want to perform velocimetry in turbulent reacting flows, and mainly some of the particular problems that we're looking at. Okay. So we'll define the needs and goals of velocity measurements, survey of existing approaches, talk a little bit about challenges with the reacting flow measurements, because there are certain particular challenges when we have reaction and heat release. We'll move in, really kind of set the stage for the final 2 lectures of the day, where we'll talk about particle image velocimetry, and kind of give a slight historical or just kind of an anecdotal of why it's become the de facto measurement, mainly all the positives with this measurement technique. Okay. We talked about this in general last lecture of why we want to look at the flow field. The flame will interact, if you will, with the flow turbulence. As one example, here's an image from DLR in Germany, where you can take this is a PLIF image, and we'll talk about these in simultaneous measurements throughout the week, but let's assume this represents the primary reaction layer, the flame front, if you will. And what you have here are the vectors from a velocity measurement, and then you show the streamlines here, or an estimation of those streamlines, path lines. And what you can see here is this is an example where you can see kind of a vortical structure, or this type of velocity folding up and wrinkling the flame. And actually, you see this really strong feature existing where we have this interruption of the flame segment. Okay? And so really we understand that flow turbulence can not only interact, it can displace, meaning it can move the flame, it can interact with the flames, it can wrinkle, or it can extinguish. Okay? And these are phenomena at times we're very interested in studying, especially extinction, reignition. Okay? And we want to understand these phenomena and how the flow turbulence ends up coupling to flame fronts, to chemistry. So again, we have this mutual interaction. When we have these interactions between the flow and the flame, they can certainly change propagation rates, rates of reaction, heat release, species formation. And again, as kind of an end user of a combustion system, a lot of these things, the stability and the pollutant output is what you care about. Okay? And you can have significant changes in the average NOx and CO that comes out based on whether the system's stable or unstable, and that can be related back a lot to the fluid mechanics. So again, we're quite concerned in turbulent combustion research with turbulence-flame interaction, and what you get in the NOMER mostly is turbulence chemistry interaction. This is just kind of a global phrase that's used a lot to say, okay, I have reaction, I have a flame front, and what's going to happen when the fluid mechanics and the chemistry intermingle. Okay? So this is kind of just a one slide that can really set up something that we probably should have already figured out. Experiments target measurements of velocity and its derivatives. And so what I'm going to do in this lecture is kind of set up why we want really kind of derivative quantities. Okay? And they actually turn out to be very difficult to measure or accurately. And then we're just going to say, okay, let's take a step back. What are some other alternatives than PIV? Okay? Again, we surveyed the class last time, and many of you use particle image velocimetry. And what are some of the other alternatives before we move into talking about that technique in detail? Okay? And again, something that we can never forget about is velocity measurements provide critical boundary conditions for modeling. In fact, simulating, trying to match data, if you will, or trying to assess whether or not data in a model output match, at times are quite limited by the boundary conditions you provide. Okay? In fact, most devices are very sensitive to the boundary conditions. So we need very good measurements so that we can provide proper input for models. Okay, let's go back to sophomore or junior level fluid mechanics. We know this velocity is a time-dependent vector, 3 scalar components. We know this. U, V, and W is the nomenclature I'll use for this Cartesian grid. Okay? And then we have the velocity gradient as a second-order tensor. So the reason why I take the time to write something that's very obvious or something you've seen for a really long time is to really highlight there are 9 components. Okay? And it's very important. We're going to see the importance or the potential importance of when we don't measure some of these. Okay? And the techniques that we have, what do we actually have access to? Okay? And that becomes important, especially when you have a flame front that's 3-dimensional. The fluid mechanics, the flow-flame interaction is highly 3-dimensional. Okay? So again, very simple. We have 9 components. Okay? Let's talk a little bit about vorticity. Vorticity describes the angular motion, okay, of the fluid relative to some center of mass of a fluid particle. If we talk about it in the context of turbulent flows, many times we talk about vorticity and eddies interchangeably. They're not quite the same. And that's kind of splitting hairs. An eddy is a statistical concept that ends up having a kind of physical presence in the flow, but let's not worry about that. Let's just say that we have these kind of structures that are rotating, and we tend to see these type of structures that interact with flames, okay? And they're quite important, okay? And we want to kind of say, okay, why do we care about vorticity? Well, if we take a step back from non-reacting to non-reacting flows, let's consider incompressible flow. Again, many of you have not had turbulence, but kind of vortex stretching is essential to the description. You can imagine if you have incompressible flow due to volume conservation, if I stretch a vortex, it has to thin, conservation of mass. But then as I thin it, it's going to be folded by the local fluid mechanics. So you get stretching and folding. You just keep repeating this process as it's being advected around. Okay? So this nonlinear interaction of stretching and folding gives rise to the structural topology, and it gives you a full range of structures created in the flow. This is what creates the topology that you see in fluid mechanics, or at least a basic topology. Vorticity we know is the curl of the velocity, and again, we end up with this definition that looks like it's going to require, we need measurements of U, V, and W, and we need them in directions X, Y, and Z. Okay? So again, the kind of same idea that we say, okay, if we want to resolve the full velocity gradient tensor, and obviously there's 9 components. Now when we start talking about the first kind of fluid mechanic phenomenon that we would really like to see, has these 3 components. And if you think real quick about what you see here, if we only have a classical planar measurement, we get omega z. That's it. Okay, we miss the other 2 components of vorticity. Vorticity can also become important in the context of the vorticity transport equation. Okay, so what does this mean? There's many ways to solve the Navier-Stokes equations. You can manipulate them and end up getting vorticity transport. You can let the dot product and entropy transport equations. Again, this isn't a turbulence modeling class, but again, there's many different ways that may be simpler or more tractable in certain ways of modeling turbulent fluid mechanics. You'll constantly see vorticity transport and entropy transport equations in the context of modeling turbulent flows. Okay? So again, if we're going to model equation, if we have to have some of these terms that are modeled, okay, we need measurements to potentially assess the quality of the models that are attempting to describe the actual fluid mechanics. Okay, so let's look a little bit at, this is a DNS out of Caltech. This is an interesting kind of show you kind of the importance of needing to look at vorticity and what's actually happening. This is just a isotropic turbulence. We have flow. These isocontours are the reaction progress variable. Reaction progress, low means 0 is pure reactants, 1 is pure product. So you can see basically we have reactants moving through. And what you can see is we have a high level of vorticity in the reactants. And then as we start passing through different layers of reaction, we end up having essentially an attenuation of the small-scale turbulence. Okay? And this is somewhat dependent on other parameters. Again, the strength Karlovitz number and et cetera is the strength of turbulence. But we can see here just in this DNS study, in this example, the vorticity, the flame, if you will, significantly attenuates the vorticity in the small-scale turbulence. Okay. All right, so we say, okay, if that's all that ever happens, we know that. But we can move into another experimental work. This is courtesy of Kareem Ahmed at Central Florida, where he's looking at a flow that has its bit of compressibility to it. And this is just an example where they measured that turbulence is not actually attenuated through the flame, but actually something called flame-generated turbulence. So here's an example. This is upstream. This is the flame marker. This is how he's chose to do the visualization. And you actually see an increase in the vorticity actually after the flame. Okay? And again, you can see this in the statistics. If you look at the PDFs of, again, this is essentially a normalized fluctuation. You can actually see when you're in the products, increase in the tails. Okay? And so U prime over S of L actually, the velocity fluctuation over the lambda burning velocity actually increases. So you're actually getting more kind of turbulent motion actually in the products. Okay? And so this is an example where turbulence was generated or vorticity was generated in the flame. Other importance we can think about is in the context of flame extinction. Let's look at a simple interaction of a laminar flame. This is just a flame vortex experiment, one where you take and you essentially puff, if you will, a simple vortex up and where it interacts with the flame. So this is a laminar flame segment, usually try to get it quasi 1D, and you have something maybe a loudspeaker, you know, it may be some other generation, but you generate a single vortex to actually look at its interaction with a flame. And depending on the strength of the vortex, this is one of the stronger ones, you can actually see the vortex interaction with the flame actually can break the flame segment, given enough strength of the vortex and enough resonance time. Okay? So we can see this significant interaction with a vortex and a flame. Now, if we assume that this is just one of the small interactions that occur in a turbulent flame, then we can see that vorticity or vortex-flame interactions may be quite responsible for flame extinction. So again, in order to look at this problem, whether it's in a laminar context or in a turbulent context, we really need to be able to make high-quality measurements of vorticity. Now, for a laminar situation, we can get away with kind of a planar image, just one component of the vorticity. There's not a whole lot of out-of-plane motion. There's not a whole lot of vorticity in the X and Y, I'm sorry, in the Z and Y dimensions. We have primary vortex and a principal flow direction. But again, in a turbulent flow, you can imagine this interaction can be oriented in any space in 3 dimensions. Okay? And finally, some work. This is Adam Steinberg when he was at Michigan. This is another example of sort of, it's kind of, I like this example. It's an example of you have kind of destruction and growth of vorticity. First of all, here you can see, if we take this black mark contour to represent the flame surface, you can see these outward rotating eddies actually start to wrinkle the flame. So you can see these two, let's consider this pair of vortical structures, red and blue. And they start to push up and wrinkle the flame, okay? And what we actually see, though, as we're doing this, as they're propagating through, the flame actually is attenuating the vorticity, right? The vorticity is dying a bit. But then what happens is downstream of this flame wrinkle, you actually form, you go from yellow, it's increasing in strength. Sorry, you actually get flame-generated vorticity. So what happens is, again, you have these, you kind of have 3 different actions here. You have vorticity that's actually taking and moving the flame and wrinkling the flame, these counter-propagating, creating this bulge, right, and the wrinkling of flame, okay? But then the flame itself is attenuating the vorticity, what we saw in that DNS example, but then the flame actually is generating vorticity downstream, what we saw in the second example. So you actually have 3 different interactions here of looking at flame vorticity interaction. Okay. Now, in addition to vorticity, we also want to think about straining of the flame. Okay, so what I'm going to talk about now is that the vorticity really is only going to sort of move the flame. And let's talk about this. We're not going to do the math here, but it can be shown that the strain exerted on a flame does not involve vorticity, but it's actually the fluid strain. Okay, so and so what do I mean by this? What happens is that vortices can come and wrinkle the flame, just what we saw in that last example. Okay, but the fluid strain can generate additional flame surface area. Okay, so really what you have is you have these two processes acting in combination. The fluid strain rate is basically, if you think about it, the strain can it can actually strain the flame and increase the flame area, and then the vortical structures come in there, redistribute the flame front, basically wrinkling it. Okay, so the strain comes in there and kind of gives you more flame area, and the vorticity comes in there and wrinkles it all up. Okay, so we actually, in addition to vorticity, we really want to take a look at the interaction between flames and strain rate fields. Okay, again, our strain rate tensor again has all the components of the velocity derivative, as we can imagine. Again, highlighting if we think about this, if we only have a two-dimensional measurement, your traditional planar measurement, you end up with only 4 of 9 components of the strain rate tensor. You miss out on all of these components. Okay. Now, in reacting flows, the interaction between vorticity and strain rate is a primary mechanism for energy transfer via vortex stretching. Okay. So let's think about this a little bit. Strain rate fluctuations affect heat release and scalar dissipation rate. Okay, so the latter, scalar dissipation rate, describes the rate at which mixing fluctuations are being destroyed, or a way that, if you think about the mixture fraction we described, I think a little bit yesterday, as the state of mixing, the scalar dissipation rate is the rate of mixing. Really, it tells you how quickly a scalar fluctuation can be destroyed. Okay, and what happens is the scalar dissipation rate turns out to be a key parameter in turbulent combustion modeling of non-premixed flames. For models you may have heard of, such as the flamelet model or conditional moment closure, the scalar dissipation rate is the key quantity. Okay, and it turns out that the scalar dissipation rate is directly affected by the strain rate. Okay, the fluid mechanics strain rate actually induces a certain scalar dissipation rate, which then is a controlling parameter in terms of reaction rates. Okay, so again, the strain rate fluctuations significantly affect the rate at which scalar fluctuations are destroyed. Okay. Now, the other thing we can look at is if we go into some data, which is kind of interesting. What we want to sit back and say, okay, all these things I'm saying, okay, how important these fluid mechanic concepts are, well, that's fine. We understand that strain rate does this, vorticity does this, but it's not quite that simple. If we go into there's always a resonance time in turbulent flow fields. And what I'm tying this in is that if we look at these measurements from Jeff Dunbar and Jim Driscoll 18 years ago, this is an example of a simultaneous velocity CH-Pliff measurement, and looked at the strain rate on the flame front. Okay, and this is just as a distance along the flame segment. And you can see these high values of strain. And you can see these very high values of strain rate of close to plus or minus 20,000. Well, if you go into a laminar flame calculation, this is well beyond the extinction strain rate. I mean, well beyond, order of magnitude beyond. But these segments are nice and intact. Okay, so what we know from laminar flames of, okay, the strain of the vorticity is interacting with the flame, it's not as clear-cut in turbulent flames. So what happens is that there's a resonance time, and these very large magnitude strains only last for a little bit of time, and the flame chemistry does not have a chance to respond to these very short interaction time. Okay? So you can get instantaneous strain rates that greatly exceed the extinction strain rates, but the flame and the flame chemistry, if you will, is non-responsive. There's not enough time. So again, this highlights that we really need to study this phenomenon. This was not really known that well before these measures, or at least it was a little counterintuitive that you could get these very high strain rates without affecting the flame. Okay? And so again, there's this need to really go in and measure these phenomena and try to characterize what actually can cause a flame to extinguish. Okay? We can't just say, okay, if we run a laminar flame and get an extinction strain rate, anything beyond that's gone. Okay? right? So I don't want to spend a whole lot of time on this. I want to move on to some of the other techniques. But the other thing that happens is the scalar turbulent scalar interactions are heavily influenced by the alignment, essentially the interaction between the gradients and the strain rates. You'll remember a little bit from undergraduate, you can decompose or find a coordinate system called the principal coordinate system. So we have the principal strain rates by doing eigenvalue decomposition. But this is just one. I'll quickly go through this. This is work out of Sandia. But what we really want to highlight, what I wanted to highlight here is that the interaction of the strain rate field and scalar gradients actually really influences, again, flame propagation. And so there's a lot on the screen, but the only thing I want to do is that if you look at your notes, there's a ST here, okay? This is just an example. This is a tangential flame strain, and it's positive, and all that means is that the turbulent strain rate, okay, contributes to the enhancement of the scalar gradients. So I don't want to really spend any time on what all these other graphs. You certainly can come ask me, but the one here is just an example by showing that in this turbulent premixed flame, you can actually show that the strain rate is actually enhancing the scalar gradients, okay? And so we see this kind of one-to-one correspondence between, or we see this heavy coupling between the fluid mechanics and the flame, okay? And that's all these slides, all these kind of background slides here, really trying to hammer home is that we really need very high quality velocity measurements, okay? We need very good velocity measurements because there is a direct coupling between the fluid mechanics, okay, and our flames, whether they be premixed or non-premixed flames. All right, let's now look at background on velocity measurements. Before you settle on a certain technique, let's see what's out there, so you can learn to appreciate the tool that you have. So many of you walk into a lab that has a nice PIV system. Let's look at some of the alternatives that maybe if you don't have that. Velocity measurements can be divided into three basic categories, what we'll call kinematic, dynamic, and physical. And in all of these, they're not always just tied to one group. So a kinematic measurement is something that's been tagged, if you will. A specific volume of the fluid stream is marked, and the motion is monitored and recorded. So you can imagine you put like a tracer in the fluid, and you watch how that evolves, and you take that motion, and you say, from that motion, I infer the velocity, okay? So let's imagine that could be either I put a dye, watch that move, or I could spark it with a laser and generate a little plasma kernel, watch that move around, other tagging methods that I'll talk about in a second. Dynamic is a measurement that involves interaction between the flow and the measuring probe. So you have some sort of probe, and there's an actual interaction. And this interaction, whether it's hydrodynamic, thermodynamic, or magnetohydrodynamic, gives you the information. Well, a pitot probe would be considered kind of a dynamic tube. The velocity is a function of stagnation pressure ahead of the probe. And then we can have physical. You can have natural process in the flow whose characteristics depend on the velocity. So you're looking at the response and indirect measurement. And again, a hot wire is an example. A hot wire, which we're going to talk about in a second, it has a dependence of convective heat transfer on velocity. Okay? All right, pitot probe. There's no reason we're not going to spend a lot of time on that because the bottom line is you can't really use a pitot probe in a flame. But again, I want to give you the background on kind of the evolution of really what there is out there. And maybe you're not working in a flame, but you want to have some sort of appreciation for some of these other measurement devices. Many of you from undergrad have used a pitot probe for wind tunnel applications. We're really not going to spend time on this, but it's a simple device to measure stagnation pressure. You can also, if you have a pitot-static probe, really what it is, it's a tube with one open and one closed end, and you have the open flow facing the flow, and the other is connected to a pressure recorder. And you use Bernoulli's equation to approximate the fluid speed. So the only thing we wanted to say, okay, is if we have a pitot probe, it can be used in incompressible or compressible flow. You just have to know how to analyze the data. In general, it's not a great idea for turbulent flows. But if the tube is smaller than the integral scale and you perform a lot of detailed calibrations, you can actually get a reasonable set of statistics. Okay? Only provides data at a single point, and if you cool it, it can be used in high temperature applications, i.e. a pitot probe is usually found on an aircraft, right? They get pretty hot. Put it on a MiG, it gets pretty warm, okay? But you have to cool it, but not flame temperatures, okay? So put a big X on here, we're not going to use pitot probes in flame. Now, we're not going to use hot wires either, but you can't talk about velocity measurements in turbulence without looking at hot wires, or at least talking about them. If nothing else, I'll take 3 minutes of your time to give you historical context of where essentially everything you'll see in turbulence comes from. Well, first of all, let me take my little sidebar. Pretty much everything when we get models or scaling laws in turbulent combustion, they all really have come from non-reacting turbulence. Not a whole lot of new stuff has been done in combustion. We actually take stuff from non-reacting and just sort of force fit it, okay? And everything that's really come from turbulence, if you will, measurements are all really made from very nice measurements in the 60s and 70s, and they were used hot wire anemometry, okay? So let's at least try to have an appreciation for how these measurements are done. You may have used a hot wire. How many of you have used a hot wire in your lab? There you go. How many of you like using the hot wire in your lab? Absolutely not. You do? Somebody started to raise their hand, right? Okay. Yeah, they're paying. So this is kind of the backbone of classical turbulence research. But let me ask you something. Why did you use a hot wire?
So it was actually an undergraduate fluids lab.
Okay, so you had to.
Yeah.
Okay. Who has used it in their research? Why? Why did you use it? Okay. Right. And it is actually the best you can do. In terms of turbulence statistics, it is the best measurement you can do. Okay? So it has by far, if it's properly calibrated, it is by far the best measurement for turbulence. Okay? So again, high frequency response. You can get time resolved measurements at a point or series of points. So we get spectra. But now let's just talk a little bit about how it works. Because actually it turns out, even in combustion research, we actually go back and we use hot wires. It's the best way for getting your boundary condition. Okay? So if you have a burner, okay, and it's in the non-reacting portion, right, characterize your burner with hot wires. Okay? Much more accurate than you will get with PIV. LDV can compete, which I'll talk about next. That's our first laser measurement. But hot wire is very good for getting very accurate turbulence statistics. Okay? So it's based on the dependence of the sensor heat transfer on fluid velocity, temperature, and composition. This is why it is really tough to use in anything other than a single fluid like air. Okay? There's a dependence on the heat transfer on temperature and composition. Okay? I'll talk about how you can use it in a non-isothermal flow. So the sensor is a thin metal wire that has a high electrical resistance, and it may be a material such as tungsten, rhodium, or radium. Okay? The wire temperature, it's a hot wire, it's at a higher temperature than the gas temperature. Okay, so we have this wire that has a current going through it, so it's really hot. And then there's a few different ways to operate it, which is not important right now, but it can be operated in constant current or constant temperature conditions. It's just how you analyze the data. Okay? So there's a thermal balance written. Again, ultimately we're trying to say, okay, we're after velocity. A thermal balance is written to where we actually have the joule heating of the wire, so we put a current through it, we heat up the wire, but then we have the heat that's removed due to forced convection. So again, imagine we just have a simple wire, we have our flow coming up through it, we're going to remove heat through convection. Okay? And then we have Q other, that's just all these other losses, and we typically ignore them, so we just have a balance between the wire that we're heating and the amount of heat that's taken away due to convection. Okay? Now, this is why kind of hot wires are a pain, is that the forced convection depends on the heat transfer coefficient, which is a function of the flow velocity, and you really need to calibrate it, okay? And you need to calibrate it well, and the calibration doesn't always hold for very, very long. So you end up, the output voltage that you're measuring, this E term, is related to the flow velocity via this A plus BU to the N, okay? Now, we have all these other things we have to know. We have to have the resistance. And then we have constants, of course, that are properties of gas. They change for every gas. And they're hard to completely characterize if you have kind of a mixture of gases. Okay. So again, kind of the way that the data is looked at as calibrations are carried out as a function of known properties. So again, you have to calibrate, and you end up finding that the output voltage is a function of U, and then therefore you can relate, this quantity S, which is just the derivative of the voltage with respect to the velocity, which is essentially just a derivative of your calibration dependence on U. If you do that, again, remember, we're only after statistics with a hot wire. You can't see anything. You can't visualize anything. So what you actually do is you end up measuring fluctuations in voltage, okay? And they're related to the actual fluctuations of velocity. Okay, so all that's fine and dandy, and that's how you end up getting your turbulent statistics. Detailed calibrations, you measure fluctuations in voltage, you turn them into U prime and U prime RMS. Okay? Now you can make these things even more fancy. You can put multiple wires, typically like in an X-wire configuration, tilt it, and now you can start measuring all the transverse components. But then the output voltage for every single tilted wire is a function of all the different directions as well. Okay, so alignment is quite important. This is an example you have in your notes. I'm not going to really go over this, but here's how you ultimately get out your measurements. You end up with a set of 3 equations and 3 unknowns, right? Because if you take and tilt a wire, it's going to be a function of the U prime and V prime. It's going to be a component. It's going to be a function of the 2 components of the plane in which it lies. Okay. And then so you need a whole bunch, you need multiple calibrations, but once you do that, you have 3 equations, 3 unknowns, and you get very nice turbulent statistics. So what about reacting flows? Okay, all this is a turbulent combustion, and we're going to get to laser diagnostics, don't worry. We just want to understand why we really want to spend the effort on laser diagnostics, because they are quite an effort. So what about reacting flows? Well, first we would need for a hot wire material that could withstand the flame temperatures. Most common materials oxidize, and they form nasty oxides. But what you would find, the biggest problem is that the hot wire is sensitive, since it's a function of heat transfer, that's the underlying principle, it's tough to separate out the velocity fluctuations that would come from the convection and just the temperature fluctuations that would come in non-isothermal flow. Now, for non-isothermal flows, you get, again, temperature and velocity fluctuations. And then you go back and you end up with something that's just quite complicated. The fluctuation in the voltage is a function of the velocity fluctuation, the temperature fluctuation, and you hear the correlation between U prime and T prime. So you can already see there that we have multiple unknowns in a single equation. So it's a tremendous amount of calibration. Okay? And it's a tremendous amount of calibration that has a lot of uncertainty in non-isothermal flows. Okay, so now we've seen where our probe techniques sort of fail. Now let's move into probably the first laser diagnostic measurement that was applied in turbulent flows, and one that's still used today. So we'll look at our hierarchy. I'll go ahead and state you cannot do a better measurement than LDV. Again, if you're interested in turbulent statistics, now in reacting flows or non-reacting flows, you can't do better than LDV. Still better than in any of the PIV. And let's talk a little bit about how LDV works. It was first introduced in 1964, okay? Shortly after the laser. Not that month, but a little bit after, okay? So how does LDV work? So the same consideration as PIV that we talked about yesterday in the introductory lectures. It involves seeding of the flow with particles. Okay? You're going to illuminate with laser light. You're ultimately going to look at the scattered radiation, but different. We're not collecting an image. We're actually interested in the Doppler shift. Okay? And so the Doppler shift is what gives us our velocity information. So we need to somehow measure the velocity shift and infer velocity. There's a lot of benefits. It's not intrusive, so now we're introducing a laser. Combustion's not a problem, no more than any other diagnostic that's thrown into combustion. It comes with the same kind of issues there, but other than that, there's no extra issues. Beam steering is kind of a problem. Most accurate velocimetry approach. It is calibration free, and we'll talk about that. Very high data acquisition rates and very good spatial resolution, and we'll see all that within the technique. The limitation, complicated and expensive equipment. That's the standard line for all laser-based measurements. We have to seed the flow with particles. Again, so this is not a seedless technique. It's a single point measurement, and it's difficult to acquire measurements near surfaces. Okay, so LDV operates on the concept of the Doppler effect. Everyone here is probably familiar with the Doppler effect, either from physics or Big Bang Theory. Hopefully everyone has seen the episode where he dresses up as the Doppler effect. If not, you know, he demonstrates the Doppler effect. And so anyway, the Doppler effect is we know this in the context of sound. Everyone knows the classic example where if I'm standing as the ambulance goes past me, we see it here a change in frequency. Again, as it's approaching the observer and as it leaves the observer. Okay? And so we see a change in pitch, high to low, as an object moves away from us. But we also have this exact same effect with light. Okay? So, but we also have this effect twice, because we have to note that if we have a flow, let's say we put particles in the flow and we have a fixed detector, right? You set up a detector somewhere, right? And you have a stationary light source. The particles are moving both towards and away from the light source and also away from the detector, okay? So we actually have two Doppler shifts, okay? So when we scatter light, we actually have light that's relative to the illumination, and we have light that's relative to the stationary observer, okay? And so we have to take into account that there's actually two Doppler shifts. Okay, so can we directly measure the Doppler shift? Because if you'll recall, we'll put up the Doppler shift equation, but if you remember from physics, the Doppler shift is a direct function of the velocity, okay? It's a direct function. So once we measure the Doppler shift, we're home free. We have our measurement, okay? Well, let's see. Let's say we measure, what I'm saying is that, okay, laser has a certain frequency and the scattered light is shifted a little bit due to the Doppler effect, okay? It's at a different frequency. So if we measure laser frequency and the observed frequency, we have the Doppler shift. But let's see why this is a slight problem. The Doppler shift is typically on the order of gigahertz, and the laser frequency is approximately 10 to the 14th hertz. So really, we're trying to measure a small number from a big number, right? And that has a very high uncertainty, okay? So it's not possible to directly measure the Doppler shift. So to improve this, there was the principle of heterodyning was used, okay? And so this is basically we're going to look at the beat frequencies between two beams, and let's talk a little bit how this works. How many of you, I didn't ask, I like to ask for all these, has anyone used LDV yet in their experiments? No? Okay. All right, so let's walk you through how this works. Let's say we have a laser, and what we do is we split this into two beams. Okay? So we have an incident beam that splits into two components, 50-50 beam splitter, two equal intensity. Okay? They end up going through a lens, and they intersect at a common point. Okay? So they're coming through two different paths, and they intersect at a common point. Okay? Particles, imagine we have some flow, and we're just using one-dimensional right here. Particles are going to pass right through the volume, and they're going to scatter light from both beams. Correct? We have two beams, two different paths, create an angle 2 theta and beta. This is all the geometry. But both beams are going to scatter particles. Okay? The scattering from both beams contain a Doppler shift. But in reference to our detector, those are both different, okay? Because they're at a different angle with respect to the detector. Remember, we have a stationary observer here, and this light is going this way, and this light's going this way, so the scattered light off of this beam is at a different angle. And the reason that is, if you look at this, alpha and beta are different. If you organize this such that alpha and beta are the same and you work out the geometry, then they actually end up having the same Doppler shift. But since right now, let's just say for a general case, since the two beams are coming at two different angles with respect to the detector, you have two different Doppler shifts. Okay? So really what happens is the scattered beams are no longer, because the particles are moving with the velocity, the scattered light is no longer at the incident wavelength, or the frequency of the light has been Doppler shifted, okay? And so there's ones at frequency f plus delta f1 and ones at delta f2, okay? Whatever these small Doppler shifts are, okay? But the Doppler shift we just established is much, much smaller than the frequency of the original light. So really the scattered light waves are pretty near the same frequency, okay? Before I hit the next bullet, has anyone ever you almost have to embarrass yourself a bit, but have you ever sung with someone and you're just a little bit off and you hear the humming? That's the beat frequency. So that's actually what we're going to take. If you sing perfectly on pitch and harmonize, you don't hear this. But if you're just a little off, you hear there's an actual beat frequency. I do this all the time because I can't carry a tune and my wife can. And when we sing, it's terrible. So there's this horrible beat frequency. Actually, that means I'm doing well. It means I'm actually close. Sometimes, usually I'm so far away that there's nothing. So what happens here is when you have waves of equal amplitude, okay, remember we cut these in, we have the same intensity, so they have the same amplitude, if you will, and they're an almost equal frequency, and you impose them, say, if you think about, remember our waves, okay, and they have that omega is their frequency. If they're just slightly off, you superimpose them, there's actually going to be a modulation of the signal between these two these signals, and that's what we call a beat frequency. And what happens is the beat frequency turns out to be 1/2 difference of the two original frequencies. And we can take advantage of that because what happens is then when we record a detector in time, so we're getting the signal from the particles, you can imagine particles are coming through the probe volume and we're getting light, right? And we're getting light at some rep rate that we're choosing to, some acquisition or sampling rate. But that signal has imposed on it a beat frequency at delta F1 minus delta F2 over 2. So that is actually the Doppler frequency. So imposed on just the data rate that's coming in, there's this second frequency that's superimposed over it. And that's the beat frequency. Okay? And then so what we can do is we can separate that out with signal processing, and you end up finding that the difference between these two frequencies, or the beat frequency, is related to this, essentially the velocity. This v here is the velocity vector times cosine alpha, which is just from geometry. So we actually can get, by measuring the beat frequency, we can get the velocity, okay? And that's how the principle of LDV works. Well, there's a second way to interpret the signal. You can think about it in a different way if you don't like the beat frequency. These are the same analogs. These are same way, just a different way to describe it. Let's say you have two beams that are from the same source. Well, they're coherent, right? It's from the same source, so they share the same coherence, right? And so the scattering from one beam has to be then coherent with scattering from the other beam, okay? So again, these are the same laser. They have the same coherence properties. So what happens when two coherent beams cross, they essentially create a grating, or we can call it an interference pattern here. And the interference pattern, which is essentially alternating zone of constructive and destructive interference, again, bright and large, and this is actually what it looks like. I'm sure you may have noticed this if you have lasers in the lab and you have them cross, you can actually see this. You can actually see this light and dark pattern as long as they're coherent, mutually coherent. And so you have this interference band, okay? So the fringe spacing that has to come out of this is a classic grading equation. It's just related between alpha, which is the angle of intersection, and the wavelength. So that's the fringe spacing, df. So as particles cross the interference, so this particle is going across, you're going to see light, no light, light, no light, light. And what you're going to do is you're going to get a modulated signal. Okay? And then what happens is the fringes, basically the crossing rate is v over df, where that's the fringe spacing, okay? And that's the velocity that we're interested in. So again, this is just another way of thinking about it, is as it crosses through, you can get this modulated signal. Okay? It's really just imposed with a beat frequency. Okay, now let's say all of that is to get one component of the velocity at a single point. Now let's say we wanted to get more than one velocity component. We would need 2 or 3 laser systems and a corresponding number of detectors. And here's an example where you have, this is a 2-component LDV system. Okay, so you have to have 2 lasers. And they can get quite complex if you want 3 components. However, the measurement is still at a single point in space. And so that's why now, moving beyond turbulent statistics and flames, or just turbulent flows in general and flames, field measurements are highly desired. And there's been a significant amount of development over the past 30 years, really to move to planar imaging, planar measurements, which is imaging, that's measurements in 2 dimensions, and then more recently to volumetric measurements. Okay, before we go there, though, let's look at some of the measurements that have been done that actually still are quite useful. And again, I use a lot of this data, we use all this data to reference our measurements to this day. Here's a flame that we've worked in a lot. This is DLR turbulent jet flame. It's just a mixture of methane, hydrogen, and nitrogen. It's a standard flame in what the so-called turbulent non-premixed workshop, which is one of the satellite workshops that we have a lot of collaborative efforts. And all the velocity measurements to date that have really used to characterize this flame, both the mean RMS and then Reynolds stress here, the correlation between U and V prime, have been done with LDV. And because the measurement is absolutely outstanding for statistics. Okay? Well, you can also translate your probe volume, and you can actually get mean and RMS fields, right? Because if you can get a measurement at a point, then I can move and get my statistics there, my statistics there. And this is a model gas turbine also at a DLR, a swirl combustor, if you will, where they've actually done LDV measurements and moved their LDV measurements around to actually characterize the statistical flow field. Okay? So you can get very nice measurements. Again, if you want very high precision, again, you'd want to use LDV. Okay? So let's look at a summary. LDV uses a continuous wavelength laser, okay, focused to small probe volume. It is a point measurement. It takes advantage of the Doppler effect to measure velocity. It's very accurate. In fact, it would be, from the laser-based point of view, it's the most accurate measurement for turbulent statistics. It can be used in the flame. The same thing that we'll talk about for PIV, the seed particles must survive flame conditions. A benefit is that the measurements can be performed at very high sampling rates, and you can get single-point time spectra. And again, if you want to measure multiple components simultaneously, you're going to need multiple wavelengths. The most common are to use dual output from an argon-ion laser. You can use CW, YAG lasers, or conventional He-Nees. Okay? Now, one thing that we didn't talk about at all is the signal conditioning and processing. That is actually kind of the devil in the details part of LDV. Okay? Once you collect the data, how do you actually truly turn it into velocity? And that is a major effort in LDV, or that's a major area that one has to have significant calibrations and make sure that's right. Okay? So this is critical to deduce accurate measurements of velocity. Okay, so our final two slides before we take a break to move us into PIV. We want to move into sort of field techniques, if you will. That's multi-dimensional approaches. We want to measure structure. We want to measure some of these derivative quantities. And there's three primary field techniques for measurements, that can be anything from 1 to 3D. And when I say 3, basically, again, any of you that have other ones, I'm happy to talk about them, but we have a technique called planar Doppler velocimetry, which I'm not going to spend more than each one of these only a half a slide on. Molecular tagging velocimetry. Then we'll spend the next 2 lectures actually on PIV. And then the first lecture tomorrow is something that we've been working on. My group is optical flow, both old and new, discussed lecture 7. Okay? So, planar Doppler velocimetry. What is this? Okay, so it takes advantage of the Doppler shift, but it doesn't work like LDV. So here's a very simple setup. Let's imagine you have a laser light. It goes in, you put it into a sheet, you scatter light. The light can be collected and it can be split here in 2 pathways, or you could have 2 cameras. Let's stick with the single camera here. Part of your light's going to go through an iodine vapor cell. I'll talk about that in just 1 second. And part of it becomes unfiltered. So we have the reference image that does not go through this vapor cell, and we have the image that goes through the filter cell. Just imagine we're taking them back to back. Okay? Okay. Now, if I have a cell filled with iodine, iodine has a structure, a spectral structure, and one component of it will look just like this. It's its own spectra that has peaks and valleys, but let's just say we have one transition here. Now let's say we have a narrow line with laser, okay, that's basically a stick here that we can move anywhere we want to. This will be the basis of, if you've looked through the lectures, of filtered Rayleigh scattering that I talk about later that we spend a lot of time on. But we can move this single line, let's say this narrow line with laser is infinitesimally thin compared to the structure, we can move it anywhere we want to, okay? So let's say I set my laser here on this edge of this feature such that about half the light's getting blocked, okay, half of it's not. The reason why it's getting blocked, this is iodine absorption, and the light that's emitted from the particles gets absorbed by the filter, okay? It has absorption bands, okay? So this feature right here will absorb the line, okay? So imagine if I put my laser line here, all of it gets absorbed, and as I move it out, less and less of it gets absorbed, okay? Now, if I'm in a flow, this is typically used in high-speed flows, there'll be a Doppler shift, okay, to the particles based on the flow velocity. That means that the actual emitted light goes this way or this way. It goes right or left depending on whether it's a positive or a negative shift, okay? Now, if I've calibrated this right when I have no flow, just absolutely no flow, I get a reference image, and then I get a certain amount of light that passes through the iodine vapor. Let's say half. It doesn't matter what it is right now, okay? Now, when I actually have flow and crank up my velocity, the reference image never changes because it's the part that it hasn't gone through the cell. And whether we Doppler shift by a gigahertz, 10 gigahertz, the camera doesn't care, right? But the part that has a filter on it, depending on which way you shift, you'll get more or less light actually make it through that camera. And so the ratio of the intensities is a monitor of the Doppler shift. And through, again, calibration, you end up finding the velocity. And you can get it in a field. So you get essentially a intensity ratio at each pixel of your flow, and you can reconstruct a two-dimensional image. Now, it sounds great. It's actually really good for high-speed flows, like hundreds of meters of seconds, because the Doppler shift is, again, only a small quantity. And so if you're talking about more like what you use in laboratory, even a lot of just even industrial that may not have this large convective velocity, the Doppler shifts are very small, and it's a very inaccurate measurement. Okay? All right. What about tagging techniques? How many of you are familiar with tagging approaches? Any of you have done tagging approaches? Or say these are kind of cool. These are kind of fun. These have a write and read step. Okay. So let's think about a flame approach right now. These can be done. These are also more commonly used in high-speed flows because typically there you're looking for an environment where you can't do PIV. And that'll be talked about a lot in the PIV lecture. But let's say this is from Bob Pitt's group, Vanderbilt. So what happens, you have a flame, let's just say, if you will, and you send a laser line to, a gridded line, so typically you have an optic that splits your sort of beams into kind of like a grid. You come in from multiple directions, right? Let's say you take your beam, you split it through all these kind of micro lenses and 2D arrays. You end up with a grid of lasers that comes in, okay? And what they do is they will do something to the chemistry, and let's just say phthalicize or knock off some molecule. So typically if you have a flame and you have a whole lot of water in it, or the easiest thing to think of is you have a flow that's in humid air. We just have humid air. We send in a laser beam. This can look very far in the UV, so it can phthalicize this process pretty efficiently. They come in and you generate OH. You actually generate because you knock the OH off of the water, okay? And then what you do is that's the right step, if you will. And then later you bring in the same thing for laser-induced fluorescence. You would bring in the 282 laser beam in, and you take an image of the beam. Okay? And so you can do this at separate delta t's, if you will, and you can have your initial grid, and then you look at some time later how the grid actually has evolved as a function of time. And then you try to find how much this one moved to this one. And displacement over time gives you a velocity. Okay? So this is a method that's been kind of put forth in very high-speed flows where you can't do PIV, where, again, let's say you have a supersonic wind tunnel that has a bit of moisture in it, you certainly can do this technique. But you can see that the problems without going into it is you have a very kind of sparse grid. How you determine how much something moved is subject to debate. I mean, are you using the middle of the line? Are you using the corners? I mean, what do you do? Do you try to do this with cross-correlation? And so it has a certain level of uncertainty of how you evaluate it. But it's kind of a fun technique for you guys to go read about, in your own time. Okay? And that's it, because what that leaves us with really is sort of the de facto measurement in a lot of in fluid mechanics, turbulent fluid mechanics, and in turbulent combustion. And that's what we'll finish today, talking the final 2 lectures, the ins and outs of PIV, how you set up an experiment, all the uncertainty in the experiment, how you analyze the experiment. Okay? And so since it's, yeah, we have time for questions based on what we did here. Does anybody have any questions? Or are we just ready to get to the next lecture? Yes. Oh.
So with the LDV and PDV, you're seeding it with a particle, and I assume that your signal is going to be dependent on your particle size.
Yes.
If you've already characterized your flow field, you know your statistics, would it then be possible to try to back calculate particle size if it varies?
Not from, you can get that from a technique called PDPA. It still uses a Doppler effect. Yes, but a different type of analysis. You wouldn't use it from an LDV construct because the LDV is just really trying to look at those frequency components. Okay, but there is a way to do this with particle sizing, and they certainly in very similar principles. Okay, so yeah, you're very close. Just not with just not with LDV processing, but there is certainly a way to do this. Other questions? Yes. Sure. So if you have non-rotating flow, there's no method to now you can have an instability. That's different, right? So, but for a non-rotating flow, the only thing you can do is you can't. There's really no mechanism to wrinkle the flame. There's nothing to displace it. There's no fluid mechanic event to stretch it. And that's in some ways what you. Well, I'll leave it at that. Yes. So non-rotating flows. Which you clearly would not have in turbulence, but in a laminar flow with no rotation, well, then you have no vorticity. Now, I will say this: that doesn't mean that you can't measure vorticity, but then it's not actually vorticity. So you probably maybe remember that there's 2 components of that definition of vorticity is not actually the definition of a vortex. If you maybe some of you remember that, is that that's just a measurement of flow that has sort of circulation that actually can just come from the divergence of the flow field. And so, and the actual turbulent eddies that we're talking about are the actual rotating structures, okay, and they have to be separated out. But again, for the most part, the vorticity is a good characteristic of the actual rotating fluid. But you're right, yes. For an LDV system, yes, you have to collect it with a lens. So what it is, it's a lens. There's usually some optical conditioning, but then it's just a simple PMT, photomultiplier. And then what you're doing is then this goes through a lot of signal conditioning. That's the part we did not talk about. That's a part that's really the most important. That's where when you buy an LDV system, if you buy one, really pay for the really nice signal conditioning and the processing. That'll take care of all the stuff versus you having to figure it out yourself. I have used systems in both ways, and one is a nightmare and one is not. How about that? So. Other questions? Okay, well, we'll take a break, and we'll meet back at 3:15. Thank you.